Great. So that's the second week of our course. We will be dealing with Introduction to Data Analysis and Linear Regression this week. And here's the outline of our second week. We will start with a summary of the last week. That's going to be around 10 minutes. Each week we will be doing that. We will summarize the content of the last week, and then we will continue with the content of the week. Then we will see an introduction to data science libraries with Python. That's going to be a hands-on training for the course, and then we will see a brief motivation for linear regression. Then we will start working on derivation of linear regression equations. That's going to be the mathematical part of today's course. And then in the last lecture, in the last 1 hour, we will be working on hands-on linear regression with Python. So let's see what we have seen last week. We have seen that artificial intelligence is this big circle that's covering machine learning, data science, and deep learning. And we have seen that machine learning is mathematical and statistical tools we use for data analysis, data science, and artificial intelligence. So there is an intersection between artificial intelligence and machine learning. Although the name of our course is machine learning, we will be dealing with some artificial intelligence stuff, especially at the last month of the course. So we have seen types of machine learning. We have seen that there is supervised learning, unsupervised learning, and reinforcement learning. If we have training data, then we call this type of learning as supervised learning. And then if we don't have training data, we call this as unsupervised learning. In the supervised learning, we create a mathematical model by using the existing data. And in unsupervised learning, we just use the data for example, dimensional reduction or clustering. And we have seen that reinforcement learning is some sort of different from supervised and unsupervised learning. This is learning by mistake, like how we learn to walk, for example. We fall, we try again, we fall, we try again, and in the end, we learn how to walk. Then we have seen which languages are being used for machine learning. We said that Python is the most popular language for machine learning, and then there is Java, C++. And we have seen the ecosystem for machine learning. On top of the ecosystem, we have Python. Then we use TensorFlow, Keras, Torch, R, and inside Python we use some libraries that we will be seeing today. We have seen that there are 3-4 major companies there that are doing the development for the deep learning, especially deep learning libraries and machine learning libraries. The most popular ones are Google. Microsoft is having a collaboration with OpenAI right now. They are trying hard. Facebook is a big shot, Amazon is a big shot as well. But from my point of view, right now, Google is the best. And we have seen what skills a data scientist must have. We have seen that you need some mathematical and statistical background for being a data scientist. And we have seen that you need some programming and database knowledge. And then we have seen that you need some communication visualization skills and some domain expertise and domain knowledge and soft skills in order to become a good data scientist. So this is the quiz for the last week. Let's go through that very quickly, and then we will be starting today's lecture. The first question was, which of the following can be considered as the father of AI? We have seen that Alan Turing may be considered as the father of AI. At least among these 4, Alan Turing would be the best answer. AI enables machines to think. That's supposed to be true. Which programming language is the most popular for machine learning? We have seen that it's Python. TensorFlow is developed by Google. That was a pretty easy question as well. Branch of machine learning that uses labeled data. That's supposed to be supervised learning. Some of you couldn't answer that correctly. Branch of machine learning that uses biological inspiration. That's supposed to be genetic algorithms. pandas is obviously a data science library that we will be dealing today a lot. Which of the following is not an AI application? Book binding. Which notebook can be used to generate fake data? Which network? It's generative networks, and CNN is convolutional neural networks, not a television channel. Okay, so that was briefly what we have seen last week. Do you have any questions concerning the last week before we start today's content? So I assume that's all clear. Okay, so the first minutes of our lecture we will be dealing with Anaconda installation and creating a virtual environment. If you didn't install yet Anaconda to your computer, please try to install from this link. Once you go to this link, let us do that. You will see something like this. You'll just download it and then you can just install by saying next and next. That takes some time, so I'm not going to go through all of that stuff. Let me. Once you install it, you will see something like this, Anaconda Navigator. This is your main screen for using Anaconda. So if you remember from our previous lecture, we will be using Anaconda in order to use Python, basically. And we will be using some virtual environments so that we can install our libraries into that environments. So once you have this Anaconda Navigator installed on your computer, you can see the existing environments here. You see I have quite a few environments here. This is the base environment that comes with Anaconda. So if you install anything to base, then you can use it from your other environments as well. And this one is the environment I usually use for the lecture. Now let's create an environment to see what happens when you create an environment. So in order to create a virtual environment, you click this plus button and then you just give an environment name. It asks you the Python version that you need to install. Let's say, okay, I'm trying to write something. So this is going to be our new virtual environment. It takes a little bit time, but once it is created, you will be seeing all the installed additional libraries that comes with your virtual environment. So it's going to be installed a little bit later. So it's being prepared, as you see here. Once it is installed, we will be installing some libraries like pandas, numpy, and other stuff. I'm not going to go through all installation process. That takes a little bit time. You should do it by yourself. I will just show you the critical parts of installation process. Okay, so now we have our virtual environment, and you see the installed libraries. And once you click here, you can just see all the libraries that potentially you can install. And then, for example, we would like to install pandas here. You just write pandas. And you see here, pandas, high performance, easy to use data structure and data analysis tool. You just click here, and then you click apply. Then pandas is installed on your virtual environment, the newly created virtual environment. I'm not going to go through all the installation process, but you need to install basically pandas, numpy, seaborn, and matplotlib in order to follow this lecture. And in the slides, you will be seeing what you should install actually. Then you can take a look at that at some point. And then we will be using Jupyter Notebook for our lecture as an IDE, Integrated Development Environment. In order to install Jupyter Notebook, you need to install some libraries. You need to install these MB Conda kernels and then IP widgets in order to use the Jupyter Notebook. So what is Jupyter Notebook? Let me talk a little bit about that. I'll be switching to my machine learning virtual environment, which is containing all the libraries that we will be using today. And once you install all the stuff that I've shown you in the slides, like this MB Conda kernel and IP widgets, you will be seeing this Jupyter Notebook. If you would like to use some stuff from Anaconda Navigator, you just say launch, or if it is not installed yet, for example, PyCharm Professional is not installed on my machine learning environment, but PyCharm Community Edition is installed. So you see, for the installed stuff, you can see the launch button, and for the stuff that's not installed yet, you see the install button. So my Jupyter Notebook is installed, therefore I can just launch it. So this kind of error is normal with the Jupyter Notebook. Don't be scared. So the Jupyter Notebook is something like this. This is basically my hard drive. And from my hard drive, I will be opening our first project. That's the Iris project. So what is Jupyter Notebook? That's basically an interactive notebook that you can use for writing Python code for our machine learning stuff. So let me add some cells. These are the cells that we'll be using for writing stuff. And there are types of cells. For example, this cell is supposed to be used for coding, as you see here. That's for code. If you switch this to Markdown, you can just write any text here. And once you press Shift Enter, that's being processed. And this is stored as a text. So if you write any Python code here, for example, let's say print hello, and if you would like to execute that, you just press Shift Enter, and as you see, it says hello. And if you would like to add any cells, you just press this. If you want to remove any cell, you just press this one. Then it deletes it. If you would like to save what you have been working on, then you press this button. That's basically it. If you don't want to use the shortcuts, you just say basically run, and it runs whatever the content of that cell is. If this is a markdown, when you say run, then it just displays the text, and if that's a Python code, then it tries to execute the code. So Python is an interpreted language, which means it doesn't compile, it is running in runtime. Therefore, if you write something in Python, you can have an error in the runtime. So you should be really careful while using Python. That's one thing I need to remind you. So what you can do with Jupyter Notebook, as I said, you can write text, you can write Python code and execute it, you can store it for later usage. For today's lecture, we will be starting with Iris project. That's basically a small application that we'll be using in order to get familiar with Python, numpy, pandas, seaborn, and matplotlib, frankly. So this is our header cell. That's our header cell. This is some basic explanation that says we will be using numpy. You can even create a link here You can write text here. That's a markdown cell, as you see. And this is basically where our code starts. So in Python, you use a library by just saying import the name of the library. So if you would like to use numpy, then we say import numpy. And here you see import numpy as np means in the rest of this notebook or in the rest of this code, I will be calling numpy as np. So if I'm going to call something from the numpy library, I will just say numpy dot whatever, numpy dot do something like this. For example, np.version is giving me the version of the numpy I'm using in this computer. Similarly, if I say import pandas as pd, I will be referring pandas as pd from now on. And then if I, for example, want to get the version of pandas, I just say pandas.version. Similar seaborn .version. So numpy is our numeric library, as the name suggests, numpy numerical Python. So pandas is a fast, powerful, flexible, and easy to use data analysis and manipulation tool that will be used a lot in this course. From reading CSV files, data files, to doing some basic operations, we will all be using pandas. That's like at the heart of our course, pandas. Seaborn and Matplotlib, these are the libraries we will be using to visualize data. So for data science and machine learning, visualization, plotting graphs, that's very important parts of the process, because if you cannot display something, if you cannot see the content of data, then you cannot work on that data. So that's a very important issue, and you should be really familiar with seaborn and Matplotlib. Okay, so let us press Shift Enter in order to execute this cell. So when you see a star here, that means it's in progress. And once it is done, you see the cell number here. So that cell was processed. And we actually imported the libraries we will be using in this lecture. So let's see what happens here. So we printed the version of numpy we are using. We printed the version of pandas and seaborn here. We printed some information. We will be printing some information about our system. In order to do that, we import system, and then we printed the system version. And as you see, it's saying that's a 64-bit AMD machine. That's a Microsoft machine. It's giving you some basic example, basically. Okay, so let's start by reading our data file. But before reading the data file, let me show you the content of the data file. Okay. So it's supposed to be here. It's supposed to be. See, inside data folder, now we are inside the data folder, we will be working on iris.data, and we will be using Notepad++ to see the content of that file. Okay, iris data. So that's basically a very long file with a lot of numbers and some text. So the numbers are the attributes or features that we will be using, and this is the class information that we will be using. So that's basically a column-wise data file. That's something like an Excel file actually, and each column is separated by a comma, and each column represents a feature or an attribute of what we are looking for. So in this project we will be dealing with flowers. That's iris flower, and this file actually is giving you some attributes about the length and width of the sepal and length and width of the petal. So there are basically three types of this iris flower. That's iris setosa, there is Iris vesicolor, and there is Iris virginica. And the main differentiation of that flower is being done by measuring the sepal length, sepal width, and petal length and petal width. Sepal is this part of the flower, and here this part of the flower, and here this part of the flower. And petal is this part of the flower, here this part of the flower, and this part of the flower. So the sepal width length and petal width length differs from type of iris plant to iris plant. So these are the features. So these columns, these 4 columns are the features, and this is the class of the flower. Okay, so how we actually read that data file? That's pandas we will be using. As I said, we will be using pandas a lot in order to root CSV files and files that are actually written like a CSV file. So this file is basically a text file, as you see. This is a text editor, this is a text file, and the columns are separated by just comma text. But the read CSV can read this kind of file as well. Okay, so Shift Enter. Now we have read the iris data file. So in order to check the data, we need to check the data as a data scientist to see what we have inside the data. If you say data frame, so when you read the content of the CSV file, it's put inside a data structure called data frame. So DF is the abbreviation for data frame. You can call anything. You can write your name here. It's just basically the name of the variable. But I prefer to use the variable df, variable name df, because it's the abbreviation for data frame. So inside our data frame, we have our data. And if you would like to see the first 5 rows of the data, you just press Shift Enter and you say data frame.head. Okay, that's basically giving you the first 5 rows of the data. But if you take a look at the data, there's something wrong. You see, this is supposed to be the column names, and these dark colored numbers are supposed to be the row names. But as you see from our data file, the first row is basically the first row of our data, which means pandas is using the first row as the column names, and we should actually prevent that. And in order to prevent that, you just say header none. That means in the data file I'm using, I don't have a header row. So if I had some text here, then I was going to have some header inside our data file, but I don't have a header. Therefore, I need to use header none. And when I say header none and check the head of the data frame, then I see the first 5 rows of the data file. Okay, so we loaded our data. Now we have seen the first 5 rows of the data, but we don't have any column names for the data. As you see, it's saying the first column, the second column, and the 5th column. And the column numbers are starting from 0. There you should be really careful. And if you would like to assign column names, you do something like this. You say, okay, the column names are supposed to be sepal length, petal width, petal length, petal width, and class. And then you assign this variable, which is column name, to the data frame.columns. And when we check the head of the data frame here, as you see, we have the column names we assign to call name variable is being displayed on top of our table. So this was data frame.head was being used to display the first 5 rows of the data. If we would like to see the last 5 rows of the data, we just use data frame.tail, this expression. So I press Shift Enter, And then, as you see, we have 150 rows inside the data frame. Let's check whether that's true. If we go to the ant, as you see, we have 150 rows, and the last 5 rows is being displayed correctly as well. So the head and tail is being used to display the first and last 5 rows of the data. But if you would like to access an individual element inside the data frame, for example, let's say we would like to see the third row, first column. So let's see, that's the third row. That's the third row because it's starting from 0, and the first row, first column, that's supposed to be 4.7. As you see, the element inside the third row, first column is 4.7. So we can access any elements by doing this. Then we have data frame.describe, which is basically describing the content of your data. So it's basically saying you have basically 150 sepal lengths, 150 sepal width. There could have been some stuff missing, so that's basically an important information. And then we can check the mean and standard deviation of each column. So this row here says it's 5.8 mean for the sepal length, and it's 3.05 for the sepal width, and it's saying there's a standard deviation of 0.8, and the minimum is 4.3. That is the maximum. And then you can basically see sort of the distribution of the data here. So as a data scientist, you need to understand your data in order to make predictions. If you don't understand your data, you cannot create a model. Therefore, you need to do some analysis, and in order to do analysis, you need to either visualize your data, and most preferably you need to see the content of your data. So these are basically the ways to see the content of your data. And this is an important command as well. I would like to see each class instances. So we have 50 instances of data from this type of the flower. We have 50 instances from this type of the flower, and we have 50 instances from the Iris virginica flower. So that's basically grouping by class. Remember, that's the class name, and this is being used to group your data with respect to the class information, and that's basically showing you the number of instances for that class. So that was basically how we see the content of our data as a text, but we would like to visualize our data as well, and we will be using seaborn and matplotlib for visualizing our data basically. So you should go and check these examples yourself. This is an image I put for you guys. I actually shared you all the data and the Jupyter notebooks with you. At the end of the lecture, I strongly encourage you to check all the examples again a few times, because this is an important lecture, both mathematically and as a beginning for the machine learning. So you should really understand the content. So there are some types of visualization that you would like to use for your case. So as you see, we have like 6 columns here and 5 rows. We have 30 different types of visualization examples here. You don't always use all of them. There are basically some plots like histograms, as you see here, or this kind of plots that we will be using a lot, or this kind of plots we will be using a lot. But you should take a look. This is a heat map. This will be used a lot. This is a plot map. This is going to be used a lot as well. For your academic research and thesis, you should take a look at seaborn library to visualize your findings. So how we use seaborn library? If you say pair plots, let me start the process. That takes a little bit time. As you see, there is a star here. It basically plots a graph for every pair of attributes. For example, for petal width and sepal length, we have this plot. For sepal width and petal width, we have this plot. And petal width, that's the distribution. So in the diagonal, you see the distribution of the data. And here you just see sepal length versus sepal width, for example, petal length versus sepal width. So why that information is important? So let's take a look at this dot here. So it basically says, for this dot, its sepal length is close to 2. It's something like 2.2. And its petal length is something like 1.5. So by just looking at these graphs, you can determine, for example, what is the relationship between the petal length and petal width. As you see, there is actually a linear relationship between the petal length and petal width. So by just checking these graphs, for example, by just checking these pair plots, you can determine what kind of model you would like to use for your machine learning problem. Therefore, visualizing your data is very important. You can see a lot of stuff. For example, you can see here, if you would like to, for example, classify the type of flowers, there is some stuff here that are in between. So it's not really easy to make a separation between this type of flower and this type of flower. So these green dots are inside the yellow dots, which means it's not possible to make a separation perfectly if we use sepal length and petal width, for example. If you look at the data, actually you will see it is really impossible to make a discrimination by just drawing a line between all these features. For example, there is a mixture here, as you see, which means we cannot make a perfect separation by just using a line if we use sepal length and petal length as the attributes of our problem. So why do we use this visualization? We would like to see how separable is our data for certain attributes, and we would like to see which attributes we would like to use for our machine learning problem. And in order to make a decision for that, it's a good idea to plot your data. Okay, let's see another type of visualization that's basically called histogram visualization. That's basically giving you the number of instances of an attribute. For example, for petal length, this graph says the attribute 4.5 occurs like 9 times. And it says the attribute 5 or the attributes between 4.5 and 5 occurs like 23 times. And the attributes between 5.5 or attributes between 5.5 and 6, they occur like 26 times. This type of display is called histogram, and histograms will be used in this lecture a lot as well. So plot diagrams, these small dots are called plot diagrams. These are distributions, and these are called histograms. And these type of graphs we will be using a lot. So let me show you other type of graphs that we'll be dealing with. These are called violin plots. They are called violin plots because they look like a violin. And here you can see both the distribution of the data. So this part tells you the distribution of the data. It says the data is centered at 5. So I have the Iristotle sepal length is usually 5, this graph says. And here inside, you can basically see the density of the distribution. So the density is high, close to 5, and it's getting less and less, close to 6 and 4. And basically you can say, I don't have any sepal length that's greater than 6.1 or that's smaller than 3.9. And when you look at this shape, this is a different distribution than this, you see. And by just checking the graph, you can judge some stuff about the content of your data. And if you look at this data, for example, this is a uniformly distributed data. And this is not a uniformly distributed data, you see. By just checking the shape of your graph, you can basically understand the content of your data. And let me show you another graph type that's being used a lot for machine learning and data science. That's called box plot. That's pretty similar to the violin plot actually. You see the starting and end points are similar. That's ending at 2.1 here, and this is ending at 2.1 here as well. This is basically showing you the mean here. That's showing you the mean, and that's showing you the standard deviation of the data. And these little dots here, and you should be seeing here as well, stating the outlier inside the data. The term outlier you will be hearing a lot. That means that's basically a data that's not similar to the rest of the data. As the name suggests, you see, it's an outlier. It is not similar to the rest of the data. And here, for example, most of your data is centered at 6.2, right? And it's not supposed to have any value smaller than 5.8, but there is just one number that's smaller than 5.8. That means this is an outlier. So by just checking the content of our plots, we can basically see a lot, as you see. And basically we just show how we can use Jupyter Notebook. This was a Jupyter Notebook. How we can load data, how we can check the content of our data, and how we can visualize the content of our data for this lecture. So the basic problem we would like to solve is, we have these dots, right? We would like to create a mathematical model that is representing these dots. And the mathematical model here that can represent most of these dots is a line, right? This line passing through these dots can represent most of the dots. So if I have an income that's not that doesn't have a value, for example, let's say we would like to predict the happiness score of a person that's having a 50,000 salary. Okay, that's basically more or less here in the x-axis. So if I follow this line, then I can see the happiness score of that person is around 3.9. So basically I use the line as a predictor. This is my mathematical function that predicts the happiness value by just using the income of that person. And as the formal definition of linear regression, we have a data set, or predictions x and observations x and predictions y. I would like to find a function f basically predicting a good value for our y given an x value. So we have three types of this hypothesis. Basically, if our prediction is a real value, then the problem is called a regression problem. If y is a finite discrete set, then the problem is called a classification problem. And if y has two elements, the problem is called binary classification. You don't need to understand the details of these definitions. We will have lectures for all of these definitions. But for today, we will be dealing with regression. So, what is regression? Let's say we have an example, attributes from a patient with tumor size, texture, and perimeter. And we would like to know whether the patient is cancer, that's the outcome, and how long will he live? That's the regression problem. So if we would like to make a prediction on real values, so this is not a discrete value, like whether the patient is cancer or not. This is a real value, right? This is a number. And we predict this number by using these attributes, the tumor size, the texture, and the perimeter. So this is called regression. And if you make a prediction about a discrete outcome, then the problem is called classification. I hope these definitions are clear. Let's make another example to make the definition more clear. Let's say we have observations and predictions, x and y values. And we plotted them as we did in the previous lecture with seaborn and pandas. And what we observe here is we basically have a sort of line passing through these dots, right? So I can make a model, I can create a mathematical model which is a line that passes through most of these dots. So that is the linear regression problem. So linear regression is nothing more than finding the best dots passing through all this, best line that's passing through all these dots. Once I find this dot, let's say the dot is this line, the line is this line. For example, I don't have a y value for the x value here, right? See, I don't have any y value here, that's empty. But if I had a line here that's passing through these dots, then I would use this line as the predictor of my y value for this x value, okay? So that's basically the prediction step. And the problem I am trying to solve is basically finding a line that is representing these dots in a best way. Is the definition clear for the linear regression? Because if you understand the linear regression definition, then the mathematics will be much easier. Okay, so let's see another example. So from your university or high school physics class, you will remember the voltage is equal to the current times the resistance, right? If you have, for example, 2 amperes of current and 4 ohms of resistance, then you have 8 volts, and that's basically the multiplication of these two values. This right value is the multiplication of these two values, right? This is basic physics. Assume that we have a fixed resistance, right? 2 ohms. And we have a relationship between, and we observe that we have a relationship between the current and the voltage. If we have 2 amperes, for example, then we have 4 volts. If we have 3 amperes, then we have 6 volts. If we have 5 amperes, then we have 10 volts. We see there is a relation, and we would like to find this relation, basically. This is going to be a linear regression problem as well. So once we plot this current and voltage values, current in the x-axis and voltage in the y-axis, what we observe is this is basically a line. So V is equal to I plus R. This is the equation we know, actually, and we would like to find this equation. And once we plot these values, we see that this is basically a line passing through all these current and voltage values. So if this is a line in mathematics and analytical geometry, you know that a line is represented by this equation, right? Y is equal to a times x plus b. You should remember this formula from your previous studies, from both high school and university studies. This is like the most basic expression you would remember from linear algebra. And in this example, where we have voltage is equal to current times resistance, this expression A, which is an unknown, is the R, and the second unknown B, which is the bias term, is 0. So make this 0, make this R, then voltage is equal to resistance times current, right? So this is the equation of the line. And the problem we would like to solve while using the while we're doing the derivation of the linear regression is trying to find out A and B values by looking at the observations that we have. Okay, so let's say we have x and y values. We have n x and y values from our observations. Assume that this is the current 1, voltage 1, current 2, voltage 2, current n, voltage n, right? So this is observation, this is measurement. Observation, measurement. And we would like to create a mathematical model, which is a line in our case, by using this x and y values. Okay? So for xi and yi, so that's the, for example, second current, second voltage, or total current, total voltage. Let's say y hat a I is equal to a times xi plus b. So this is the prediction. This is observation. Yi is observation. Yi hat is the prediction. Okay. So remember, here we have observations and measurements. Observations and measurements. So this is observation. This is measurement. This is the yi hat is our prediction. And the problem we would like to solve is we have a lot of measurements and observations. From these measurements and observations, we would like to find A and B in linear regression problem. So for this problem, we have n measurements and observations, right? And the total error, if we make a prediction with our unknown A and B, is yi minus yi hat. Okay, this is the total error. But if I have this total error like this, then I have a problem. Let's say I have my measurement yi plus 5 and I have my prediction minus 5. Then these are gonna cancel each other, which means that's gonna be 0, and I don't want that. So if I use the square of the error, then I don't have this problem, right? And the problem I would like to solve for linear regression is I would like to minimize this expression. Are you with me? So the mathematics,
Yes.
is going to start now. Okay, so a small reminder from our calculus courses. If we would like to minimize a function, the minimum of a function, how do we find it? We take the first derivative, right? If we take the first derivative of the function and then we make it equal to 0. In this example, for example, the derivative of this function is t minus 1, and the minimum of this function is where the first derivative of this function is 0, and the first derivative of this function is 0 at 1. Okay, so for t is equal to 1, we have the minimum for this function. that's a small reminder from calculus. We will use this knowledge in order to minimize that function, that error function. So what we would like to minimize is this one, the sum of square errors. This is called the sum of square errors. That's basically the error between the measurements and the prediction for each observation. We have n observations, remember? We have n observations, and for each observation we have a measurement and we have a prediction, and this is the total error we could make, and we would like to minimize this function. So basically the prediction, remember from our previous slides, the prediction is this, right? We would like to find A and B. So this expression is basically y I hat. Okay. So just follow the right side of the slide. So this is the function we would like to minimize. In order to minimize a function that has two unknown values, here we have A and B as the unknown value, we need to take derivative with respect to both A and B. Okay. So if you remember the chain rule, then it's gonna be easy. We first will take the derivative with respect to A. That's basically this expression. There's two goals here. You just take this part of the equation as is, and then you take the derivative with respect to A. This cancels out, this cancels out, and this is basically coming as minus xi. Okay, this is basically the derivative with respect to A, the derivative of this function with respect to A, this expression. So in order to minimize this expression, what we need to do is actually we need to make this equal to 0, right? So this is how we make this equal to 0. So this 2 cancels out because this is a multiplication, and that's basically minus xi times yi here. This expression is making this positive. That's basically a times xi square, and that's basically minus here, minus coming from here, that's b times summation of xi's is equal to 0. So this expression is basically equal to this expression, and once you put this part on the other side of the equation, this one, we get the first expression. Okay, so this is our first formula that will be used for derivation of linear regression. So that might look a little bit complicated, but once we get the derivative with respect to b, we will be connecting these two equations, and we will see how we can gather both I and b. So remember, the problem we are trying to solve is we are trying to find out A and B by using our n observations. Okay, so we created an equation with respect to A. Then we will be taking the derivative with respect to B, the same expression, the one we would like to minimize. We have two unknowns, so we need to have two equations. We got our first equation by taking the derivative with respect to A. With the same fashion, by taking the derivative with respect to B, we have this expression. So basically the same, you take 2 here, the same expression comes here. We take the derivative with respect to B, there is no B here, cancelled out. There is no B here, cancelled out. There is 1 B here. Take the derivative of B with respect to B, that's 1. Minus is coming from here, so that's minus 1. And this expression basically is equal to the expression here. After the lecture, please go through the slides and try to prove that by yourself. That would be really beneficial. I know it's not that easy to follow right now, but trust me, you know all this mathematics. Trust me, you forgot all of that. But you had seen all of this stuff in your differential equation, linear algebra, and calculus courses. I'm pretty sure most of you don't remember most of the stuff I'm talking right now. Don't be scared. You will not be responsible from the mathematics, but try to understand, try to have a grasp on the mathematics. Okay, so this expression is basically equal to this expression, and once you take this minus some yi on the other side of the equation, then we have this expression. This is the second equation we will be using for the derivation. So now we have two equations and two unknowns. What we will be doing basically is connecting these two equations to find out a and b. So remember, the problem we are trying to find out is solving a and b, right? We have an observations. From that observations, we would like to find out the values of a and b. So I was a little bit lazy. That's my handwriting. Sorry for that. So we will make some simplifications. You see our equations here, the first equation and the second equation. In order to make things a little bit simpler, we say sum of xi squares is called c here. So this is going to be ac, like this one. We will call sum of xi's, the guy here, as d. Therefore, this part of the equation becomes b times d, and we will be calling yi times xi, summation of yi times xi, as e, which is this part of the equation as e. So this equation, then this first equation becomes this one. Okay, so this is a simplified expression of the same equation. We had a value for xi, which was d, which means this part of this equation is a times d, and this is basically b times n is equal to yi. We didn't have yi here, so we will call summation of yi's as nf. So the second equation, this equation becomes this one, right? Now we have a simpler equation. We have two unknowns, a and b, and we would like to solve the equation for a and b, and we have these definitions, c, d, e, and f. So how we will going to solve this equation? That's pretty easy. We just multiply the first row, this equation, by n, and then this part of the equation with d, and we have this equation, which is basically this equation, and we have the second equation, a times d plus b times n is equal to f. Basically, this equation is the same equation as this one, and then we subtract these two equations from each other, right? Then what we have is a times cn minus d square is equal to en minus ft. Okay, right now we have cancelled out b. That's why we did this. We first will cancel out d, and we will find a, okay? And then we will try to find b by using a. So basically, what a is en minus ft over cn minus d square. And remember our definitions from this slide. What was c, d, e, and f? If we put the definitions here, a is equal to this one. So remember what we had? We had x, y, and yi values. We had n observations, like the one here. From these observations, we were trying to find out the best line passing through that observations, and the line equation was y is equal to a times x plus b, and we were trying to find out a and b values, right? And now we have the a value. And if a value is this guy, which is our third equation, this is our basically the most important equation for linear regression. Then what b is, we just use a here, and we just use this equation, and b is equal to this one. We already know what a is. We first find out a, and then we use the value of a here with the other observation values, and we get the b from this equation as well. So this is basically the derivation of linear regression. I know that was a little bit complicated. That's not really easy to grasp. But just remember this. We have n observations, x and y values. From n observations, x's are observation values and y values are measurements. We would like to create a mathematical model, and since we are dealing with linear regression, we would like to find a line. That's, as the name suggests, linear regression. So it's supposed to be a line, and a line is defined by y is equal to a times x plus b, right? And we would like to find out the values for a and b. That's basically what linear regression is. So let's see a small example, and then I will be showing you another way of derivation with a more advanced mathematics by using the pseudo inverse of the observations. We will be using mostly scikit-learn in order to make the predictions. So you're not gonna write your own equations and use all these mathematics I have shown you, but you should understand the mathematics in order to grasp what's going on. Okay, so let's see an example. We have x values as the hours of sunshine, and we have the measurements. So this is observation, this is measurements, ice cream that are sold. So if you have 2 hours of sunshine, let's say you sold 4 ice creams. If you have 3 hours of sunshine, you sold 5 ice creams. And that's going on like this. If you have 9 hours of sunshine, then you have, let's say, sold 15 ice creams. Then we would like to create a mathematical model. That's our mathematical model. Y is equal to a times x or m times x. Sometimes this is called m, that's because it's called slope. And y is usually called as bias, that's why it's called b, but sometimes it's called as y-intercept. So both terms are slope, y-intercept, and a and bias, that they are both being used. So what we would like to do is we would like to create a mathematical model that's y is equal to m times x plus b by using our observations. These are our x values, these are our y values, and from each observation we will make predictions, and we will try to find out the values of m and b here. This m stands for b in our previous example. So remember our formulas. A is equal to this ultra complicated with a lot of Greek notations, and that's our formula for b. But what we have basically is x and y values, right? So x being hours of sunshine and y is being ice cream sold. Look at this: 2, 4, 3, 5, 2, 4, 3, 5. X and y values in the first and second column. And when you look at this formula, what we need is we need x square, right? We have x square here, and if you look at it, we need y times x, right? We have y times x here. So we calculate the x square and y times x from this first 2 columns. So we have now x square and xy. Okay, now we have x, we have y, we have x square, and we have x and y. Okay, now as this Greek notation is the summation of these guys, the summation of x values is 26, the summation of y values, we have the summation of x square values, and we have the summation of x times y. Okay, so we will just put these guys into this formula in order to make the prediction for a and b values. So what was m? M was a, right? And when you look at the formula, n is equal to 1, 2, 3, 4, 5, because we have 5 values, and we have summation of x and y, which is 263, and you just basically insert these values into this formula, and you find a or m is equal to 1.5. And remember from our formula, once we find A, now we found A actually, you put the A value here, this part of the formula, and then you can calculate B as well. So what do we need? We have the summation of Y, we have A, we need A, which we calculated in the previous slides. We need summation of X, then we will divide it by the number of our observations, which was 5 in our case. So we put the values here. We had calculated the value of M, or to say A, as 1.5, and the summation of X values was 26. We divide that with 5, and we got B as 0.3. Okay, so we calculated A and B values from our observations in this example. So that was the equation we would like to solve. That was y is equal to A times x plus b, or m times x plus b. In this case, we found m as 1.5 and b as 0.305. So we basically predicted the b and m values, or a and b values, from our observations. So that's basically what linear regression is being used for. And let's take a look at the x and y values, whether we did something good or bad. If you plot the dots, you see that this is somehow curvy. That's not exactly a line. But as you see, a line is more or less representing all these values. So you could use a more complicated mathematical model. You could use a curve in order to model this. But a line is also fine because it's passing through close to most of the points. So basically, there are some errors. You see, these are the errors of our mathematical model, but they're not too big. Okay, so it's kind of a fine fit, I would say. So what we did is we had these points. We created a mathematical model, which is this line, and then we can use this mathematical model basically in order to make a prediction. For example, for this point. Right now, we don't have any numbers. For example, if you have like 8 hours of sunshine, how many ice creams can I sell? This is the problem I can solve right now, because I now have the mathematical model for the line. So is linear regression good for everything? The thing is, linear regression is not good for everything because it's not really resistant to noise. So what I mean by noise is, look at this example, for example. Up till 4, the distribution of the data is quite linear, right? It's kind of linear, I would say. But after 4, the distance between points is increasing. And this is called noisy data. And if you have noisy data, linear regression doesn't work well. You need to have a fine distribution, something like this. If you have noise like this, then linear regression doesn't work well. So we have more robust regressors like Ranzek. That's something we will be seeing next week, that can handle noisy data. So this is noise, for example. As you see, most of our dots are accumulated around a line. And if we had a good regressor, if we had a stable regressor, we would have a line something like this. But when we use linear regression in this noisy data, then our mathematical model that was created by using these dots is something like that, which is not really representing all these dots in a good way. So this line is much better, and it's using another technique called Ranzek, and we will be seeing that in the next lecture, next week. But just remember, linear regression is not good with noisy data. Okay, so there is another way of deriving linear regression, if it was not complicated enough for you, the other method. In this method, we will be using basic linear algebra and calculus of these variables. That's something we will be using for multiple regression, which means In this problem, we were using one variable. So we have one observation and one measurement, right? We have one x value and one y value. But things might be more complicated. You might be solving more complex problems where you have more than one attributes. For example, in the cancer example I have shown you, we had tumor size, tumor texture, and there was another attribute. When you want to create a mathematical model and you have more than one variable, that's called multiple regression. And in order to solve multiple regression problem, we will be using this kind of derivation. So just try to understand that's not so easy, that's not so complicated. In the end, you will see one formula again. In the previous derivation, you had seen two formulas. You will be seeing one formula for the derived method. So the problem we are trying to solve is the same. We have n observations. We have our first measurement from our first observation. We would like to predict A and B values. Okay, we have n observations, we have n measurements, and we will be writing this equation as a matrix form. So this is an n by 1 matrix, and I need to get a n by 1 matrix from my observations. So if I write these observations in this way, I have an n by 2 matrix, right? This is an n by 1 matrix, this is an n by 2 matrix. In order to get an n by 1 matrix from a multiplication of n by 2 matrix, I need to have a 2 by 1 matrix. So this is A and B. These are the things I would like to predict. So these are our knowns, y and x values, and these are our unknowns. So if I write this in matrix notation, that's basically y is equal to x times w. W stands for A and B. That's a column-wise matrix. Y is a column-wise matrix as well. That's basically storing my observations, and x is storing my x measurements as a column-wise matrix as well. So that's a minimization problem. Again, I need to minimize this value, because remember, y is equal to x times w, and I need to minimize this. And basically, when you square this, you get the transpose of this expression times this expression, which is basically this expression. And if you remember from linear algebra course, 100% you don't, this expression is equal to this expression. So just a quick reminder about vector calculus. Most probably you didn't see that. The differentiation of these matrices with respect to x, you can get the formulas from here. And these are some reminder definitions. If you have a transpose of a matrix multiplication, then that's the transpose of that matrix B times the transpose of A. So these are some basic definitions you might be using in order to understand how we differentiate with respect to W. And when we differentiate this expression with respect to W, we have this expression, okay? And we need to solve W, right? So W here is x transpose x inverse x transpose y. So we have y values, those were our observations, x's are our measurements, that's t stands for transpose, that -1 stands for the inverse of the matrix. So this expression is called pseudo inverse. This is not an exact inverse formula, this is a pseudo false inverse of a matrix. Just remember this pseudo inverse. That's an important expression that will be that we are going to use in the next lecture. That was another way of deriving linear regression. I think this is a little bit more complicated than the one in the first part of the lecture. Just remember this expression, this pseudo-inverse expression, and these two formulas. These are the formulas. Either you will be using these two formulas in order to predict A and B, or you will be using the pseudo-inverse formula, this formula, in order to predict A and B. Remember what was W? That was a column-wise matrix. Here you have A, you have B. Okay, that looks fine. So we will have two examples. The first one is an example from Kaggle. Basically, you can find the source code and the example data file from Kaggle as well. That's basically the marketing budget for a TV and the sales example. So the problem we would like to solve is to predict sales by using the marketing budget of the TV. So let's check the example data file again. So if you remember, we have TV markets CSV. So this is a CSV file. Therefore, we will be using Excel to open this up. So that's basically the first row are the column names, and the rest is that's X values, Y values, X values, Y values. That's kind of a long example. Still X values, Y values, X values, and Y values. We will still be using pandas in order to read that file, and then we will be using scikit-learn in this example. That's yet another library we will be using a lot in this course, scikit-learn, sklearn, in order to make our prediction. Okay, now let's start. So if you remember from our previous lecture, when we press Shift Enter, that was executing that cell. We imported pandas as PD. And in the previous lecture, if you remember, that was DF, data frame. So here right now, the name of my variable is advertising. The name of my data frame is advertising. I'm just gonna read the TV marketing CSV file inside my data folder. You have that CSV file. I emailed you. Okay, now the reading is complete. Now let's check the first 5 rows of our data frame. So it was basically the data frame that had. And since we had the column names as TV and sales, we can see that column names in our data frame that had expression. Okay, so let's check the shape of our data frame. You will now see what I mean with the shape. This basically means we have 200 rows in our data frame, which means actually we have 200 observations, and we have X and Y values because we have 2 columns. We have 200 rows, we have 2 columns. So dot shape, data frame dot shape means the rows and columns. If it was like 3-dimensional, then there was going to be another comma. And if it was 4-dimensional, there was going to be another comma. So the shape basically gives you the shape of your matrix. So data frame is a matrix. So we have 200 rows and 2 columns. Okay, let's make a scatter plot. What I mean with scatter plot. So this is basically our TV budget, which is X values in our data frame, and this is the Y values in our data frame. This is basically the sales. As you see, this more or less looks like a line. That's not a good line from my point of view. A curve, a polynomial passing through like this would represent much better. But can we fit a line to this data? Yeah, we can fit a line, and it's gonna be something like this. That's probably. But this is a data with noise, so our line is not going to be really good. But if we had noise from here or here, if we had outliers, then our linear regression model would work less better. So this kind of noise can be handled by linear regression. But if you have outliers, like stuff dots here, then it's more problematic for linear regression. Okay, so we have seen the scatter plot of our data. So what we would like to do is try to predict a line. We have x values as our observations and y values as our predictions. So let's evaluate this. As you see, we have these values as the first 5 rows of our data. We have our observations, and then we have our measurements as sales. And we will put the sales column. So we put the TV column of our data frame into X here. And here we put the sales column, which is this one. You see, we have 2 columns. We have TV column, we have sales column. This is X, this is Y. And here we put TV, which is X column of our data frame into X. And here we put our sales column, which is Y, into Y. And if we evaluate this one, you see we have 20.1. You see that's correct. So that's the first row of our data. Okay, so we need to modify our data a little bit in order to use scikit-learn. In order to do that, we will use numpy, and we will somehow slightly change the shape of our x. You see, when we print the shape of x, that's 200, right? When we say xt, that's 200 by 1. In order to use scikit-learn, the shape of your data is important. So you cannot put this shape into scikit-learn. Therefore, we need to do this operation. Okay, that's a restriction for scikit-learn. And scikit-learn, as the name suggests, is a very famous machine learning library. It's sklearn. You need to install this into your virtual environment as well. And inside scikit-learn, there are quite a lot of models. And linear regression is one of the models inside the linear models of scikit-learn. In the rest of the course, we will be using sklearn for creating our mathematical models. So you should take a look at its documentation, and you need to install scikit-learn into your Anaconda environment. Okay, so let's import our linear regressor. So the basic operation we need to create a mathematical model with scikit-learn is we define the type of the model. In this case, it's a linear regression model, and then we feed our model with x and y values, and we say fit a model into this x and y values. That's same for all the models we will be using, not just for linear regression. When we use polynomial regression, that we will just change this linear regression into polynomial regression. Or if we use another regressor, we will just change the name of the model, and then we will use the fit operation. So we have model creation. We have 3 steps. We have model creation, we have model fitting, which estimates the model parameters, and then we use the model to predict stuff. So we have creation, fitting, and prediction. Okay, so let's create our model. That just created an empty model, but it knows that's a linear regression model, which means it's going to solve the problem in order to predict the values of a and b. Okay, so when I say linear regression that fit xty, that's going to use our x and y values in order to make a prediction for a and b. So we made our prediction. Now we have our mathematical model. Okay, and when we say print intercept and coefficients, that's basically printing a and b values for the linear regression problem. So let's see. Those are the values. And once we would like to make a prediction, basically, we just use this function, model name.predict, and we supply this prediction an x value. In this case, let's say we would like to find the sales for 60. Let's make a prediction. And in order to print the prediction, we just say print it's 9.8. Okay, let's see whether that's some sort of a correct prediction. So we have 60 here and we have like 10 in y-axis. 60, 10. Okay, let's look at the graph. We have 60, something around here, right? And if we take a look at its prediction, it was around 10. And as you see, it's some sort of a correct prediction, because we fit a line that most probably is passing through here, right? And then we use our line in order to make a prediction. The prediction for point 60, which is here, gave us 10. And when we take a look at the data, we can observe that the prediction is more or less correct. So that was a simple example for linear regression. We had TV sales on y-axis, and we have the budget in marketing budget in the x-axis. We used our x and y values, observation and measurement values, in order to make in order to create a line model, and we used that line model in order to create a mathematical model. Then we could make predictions. So let's work on a little bit more complicated example that's called Boston housing price prediction. Most of this data is quite common in machine learning community, so you can find most of this data online. A lot of codes that's dealing with this data as well. So here we will be using pandas with scikit-learn, and we will be using numpy again. Let's just import that stuff. Let's take a look at the data. That's a little bit more complicated data than the previous example about the simple regression. I think I have this here. Okay, that's the housing data. So you see there are quite a few columns, and it's 500 rows. It's a lengthy data actually. And let's see how we can deal with this data. And what are we supposed to do to deal with this type of data? First, let's read the data into our data frame. So now we have our data inside our data frame. So let's remember what was data frame that head was doing. It was showing us the first 5 rows of the data. So it's kind of a complicated data, I would say. We have 14 columns, we have 500 rows, and we actually don't know the names of the columns. But from some internet research, you can find the names of the columns. You see, the first column is per capita crime rate by town. So this data is basically in the last row, in the row 13, we have a house price. Okay, what we are trying to do is to predict the house price with respect to some attributes, and these are the last, the first 13 columns. These are the attributes that might be used for this problem, and we will see which attributes are related, which attributes are less related, which attributes are good to use, and which attributes are good to use for linear regression. So you may have some data like this. You have a lot of attributes and you would like to make a prediction, for example. If you use multiple regression, you can use all these attributes. If you just want to use linear regression, simple linear regression, you should just use one of these attributes. And in order to select which attribute is the best for your prediction, you need to analyze your data. And we will see how we analyze your data to make a good prediction. So these are the column names. And remember from our Iris project example, we create a variable called column name, and we write the column names here. And when we assign data frame.columns, this column name, let's do that. Now we have a better table, right? We have the first 5 rows with the abbreviations of the column names. So this is the median house value. This is the most important column. We would like to predict these guys, and these are the attributes we would like to use. So let's take a look at some of the potential attributes. For example, average room number per dwelling. That might be a related attribute that we could use. Age proportion of owner-occupied units prior to 60-40. So full value property tax rate for 10,000 bucks. There is lower status of population. That's crime rate. So we need to take a look which of these attributes are really related and which can be used for linear regression problem. Okay, so let's first describe our data to see what we can find out. So basically we see that we have 14 columns, and for each column we have complete data. We have 506 rows for each attribute, so we can see that our data is complete, and we can see the mean values for these attributes, standard deviation, minimum and maximum values from data frame describe. Data frame describe didn't give really so detailed definition. That's not very useful information for this problem. So we need to somehow plot our data. So remember we were using matplotlib and seaborn. I'm not going to execute this command. That's an execution from my previous session. That takes a lot of time, but for your case, when you study alone, please execute this cell as well. So this is basically the pair plot. And what was pair plot doing? It was creating a plot for each attribute pair. Let's take a look, for example, for the house price versus crime rate, we have this plot. For the house price versus room number, we have this plot. And we can use this plot basically to find out which attribute is more suitable for linear regression. Let's say this attribute. So whatever this DIS is, that's kind of a curve. So this is not a line actually. So this is not really good for linear regression. I wouldn't use this for linear regression. Would it give a result? Yeah, most probably you would get a kind of okay result with this attribute, but you could find much better attributes. For example, this RM, which was I think room number, this looks like a line, right? So therefore this looks like a good attribute to use actually in order to find the house price. And when you look at this L-stat, this is a curve again. So if you were going for a polynomial regression, I would use this. That's a nicer curve than this guy as a line. But since we are dealing with linear regression and we would like to fit a line, the best line would be something like this. And if we use this as a predictor, then the error between 0 and 5 would be greater. So I think RM is a good attribute to use for predicting the house price. So let's take a look at some specific examples. So we had 14 columns. The pair plots, if you don't restrict it anything, it's plotting 14 by 14 matrix. So this is a 14 by 14 plot structure, as you see. That's basically every attribute with respect to other attribute plots, which is quite complicated, but it's giving you an overview. But if you want to make a broader study, let's say we just would like to see the crime rate, Z and whatever it is, in those NOx and RM attributes, then we restrict it. We restrict our plot, and then once we plot them, you see that's a less crowded plot. So if you would like to, let's say you just to take a look at the pair plot of all the attributes, and then you basically say, okay, I would like to use RM, H, whatever this takes, and LStat as the attributes, and then in order to make a broader study, you just use that columns in order to make plots that looks nicer and less dense. So let's say we would like to plot the pair plots for these attributes. You see, you don't see any line structure here, but you see some sort of so this is basically the house price, this is the LStat attribute. This is more likely to be used because it looks like a line. This shape looks like a line, but it's really not a line. This is a curve. But the rest, you cannot fit a line. This is definitely not usable. This is certainly not usable. This is kind of okay-ish. So this is a line, and this is a line, but these are outliers. So if you use linear regression, that regressor is going to create a line something like this, and the error rate will be so high. So this is not usable as well. If you use a robust regressor, this is also okay for a linear regression. This attribute is also okay for a linear regression. But if you ask me, I have these three attributes, which one would I use? I would choose this one. But if you ask me, I have this 13 attributes, which one would I use? I would use the room number, because this looks like a line much more than the rest. So remember, we need to choose our attribute with respect to the model we will be using, or we need to use a model that is likely to model the attribute we use. Yeah, either way, either you choose a good attribute and use a simple model, or you choose just one attribute that represents your data in a good way, and you choose a predictor that can represent that data. Okay, so let's analyze our data further. We would like to make a correlation analysis. Correlation means how correlated one attribute with respect to the other. So basically, that gives you an idea which attribute should you choose for linear regression. So we are going to use pandas for correlation estimation. And we will be using seaborn in order to display the results for our result. So this is basically a heat map of correlation. That says, for example, so this is what we are looking for. We are trying to estimate the median value of the house price. And we would like to find a potential attribute that can represent this value, that's correlated with this value. So if you take a look at this room number is correlated, the most correlated value with the house value. We also have this guy that's kind of correlated as well. Negative correlation is not something bad, that's also okay. So we can use either this one or this one. So they are both correlated. But if you take a look at the pair plot, so this is the one with positive correlation. This one is the one with negative correlation. They are both high, they are both 0.7, but this looks like a line. So our aim is to use a linear regression model. So we would like to use a line basically, which means if I use this guy, my model, my predictor model is not suitable for this data, but my model is more suitable for this data. So I should use this one. But if I were to use a polynomial model, then I could think of this guy as well. So I made a correlation analysis and I found out that this attribute is quite correlated with this one. Also, this attribute is quite correlated with this one, but the shape of this attribute is more suitable for a linear regressor. So I'm going to use the room number for my study. So this is basically more or less the same analysis for other attributes. Okay, so let's take a look at our data frame head again. If you remember, so RM is this one, and we will be using this guy, and we will be using this column in order to predict the values of this column. So my X is basically the room number, this column, and I'm assigning the column into X, and let me see the first 5 values of X. As you see, these are the first 5 values of X. And if you remember, we would like to predict the median value of the house price, which is the last column. We assign the values of the last column into Y. And let's print the first 5 and check whether they are correct. See, that's 24, 24, 21.6, 21.6, they are correct as well. So now I have my X observation values and Y measurement values. So I have observation X, measurement Y. As I did in the previous example, the simple linear regression model, I'm going to use the linear regression from scikit-learn, Shift Enter. I initiate a model, that's the initialization phase. The model is just an empty model right now. There's nothing inside. No A, no B, just simple regression model. And here I had assigned the X values and Y values. I will be using that X and Y values in order to fit a line model. Just use that. And I will print in the coefficients. You see that's A, that's B. I had predicted. Okay, let's plot the line we created. So right now we created a line by fitting X and Y values, a linear regression model. So let's see whether this line is representing the dots in a good way. You see, we use matplotlib and seaborn in order to display our line. These blue dots are on the x-axis average room number, and on the y-axis the house price. So this is basically, the scattered dots are basically our data, okay, our observations. And this blue line is the line we predicted. So basically, as you can see, it's not a bad line. It's, I would say, the best, as good as it could do. And by visualizing this line, we make sure that what we created is more or less representing our data. There is another way of displaying this data, just to see the distribution of the data. As you see, the distribution get denser close to 20 in y-axis and close to 6 in x-axis. This is a representation with histogram, so that you can see the distribution of x and y values on a histogram at the same time with the pair plot of the data, and we can display the line with all the data. Okay, let's make a prediction. So we created our model. Now we should be able to find out the price of a house basically with our model. So let's say our house has 7 rooms. Let's make a prediction with that. It says the price is around 30. So 7 is here. We come here. 30 is kind of a good prediction, right? As you see, when you have 7 rooms, you usually have house prices around 30. There are some exceptions, you see, but look, there are houses more expensive than 30, but usually the house prices when you have 7 rooms is around 30. So we made a good prediction. So let's check. We predicted A and B values for our line, whether we were actually successful while we were predicting our model coefficient and model intercept. So remember, coefficient was A. So this is our line. X times A plus B. Intercept was B. Right? If you remember what we printed here, the coefficient was 9. The intercept was minus 34. So we will use this equation in order to make a prediction, and we will see whether we will be able to do the same prediction. As you see, when we use the model as a predictor, we got the same result if we use the coefficient and the intercept in our equation. So this is basically the line equation. Okay. So we have another very simple example for the pseudo inverse method. So if you remember, the pseudo inverse formula was this one: transpose of x times x inverse times transpose of x times y. So I created a function in Python. When you want to create a function, you start with def and you write the name of the number function, and then you assign the parameters. This is basically the Python representation of this formula. Nothing more, nothing less. So let's execute this. We have x values and y values from our room number column and the y values from the house value column. We reshape the y so that we can make the multiplication, and then we use our regressor. And once we execute this, we basically get the same result. It's not exactly the same. You see, 0, 4, 4, 1, 4. That's more or less same, but it's usually not exactly the same. So this is another way of solving the linear regression problem. As I told you in the previous lecture, this is just basically the pseudo inverse of our observation matrix and the measurement matrix. So we can either use this formula or the equation 3 and 4 in the previous lecture, but usually we will be using scikit-learn in this lecture in order to make our predictions. We will assign our x values. It can be one attribute or more than one attributes. We create our model. We assign our x and y values. We make a fitting operation, and then we make a prediction operation. So basically, you can read these steps for machine learning. That's from a famous book. What it says basically is you choose a model, you create the hyperparameters, you fit a model, and then you make a prediction. Okay, so is everything clear up until now? Do you have any question concerning what we did with the Jupyter Notebook? I offered you the Jupyter Notebook. Please go through that. Try to make the exercises yourself, and try to understand what we are doing. Try to at least understand this scikit-learn stuff. How we use x and y values, which attributes we used and why we choose that attribute, and try to at least grasp how we create a model, how we create an empty model, how we make a fitting operation, and then how we make a prediction. Just try to do that. You will have your first homework after next week, which will be covering all this stuff. Before that, please install Anaconda, please install all the libraries required, and go through all this stuff I provided for you. Please go through the lecture again. I will put in the video into YouTube. I will be offering the slides as well. First, try to follow the video and try to make the exercises yourself.